And I think it's been wonderful, not just to be able to bring together the theorists and data analysis people, but with the recent years, with COVID and other things, even bringing all the data analysis people in the same room has not been an easy task. So I think it's a wonderful opportunity. Let's see. Which one? This one? Okay. Sorry. I think. Okay, not working. A very good conference as the bumps.
Okay. No,
okay. Perfect. So which one you said?
The big button.
The big button.
And then the bottom is for going back.
Okay. Okay. So, okay. So this is the outline of the things I wanted to cover today. So I wanted to talk about the multi-messengers that come from core collapse supernovae. But I want to start right away with a disclaimer, which is that I'm going to focus on things we are currently using. But it is my hope that during this conference, we will also start discussing for the future other things that we could use as well. And I will not cover, for example, nucleosynthesis or polarization measurement or Doppler shift measurements, but I think it would be nice if we will find a way to discuss for the long-term planning some of these things. Then I will talk about the detector response. And obviously, for people that are in the LIGO-Virgo collaboration, some of these things are going to be pretty well known, but it's good to give a little bit of a background. And so in terms of geometry, antenna pattern, and statistical properties of the noise, and then a general description of how we approach the problem of detecting core collapse supernovae, some mainstream direction that we are using, and some new direction that we are exploring. And then parameter estimation, mentioned the deterministic feature we already started to see in the previous talks, and some astrophysical interpretation consideration. And then I will say a few words about the model selection problem in terms of distinguishing between slowly and rapidly rotating progenitors. This conference has been wonderful. So in some aspect, whenever it's possible, I will give pointer to other presentations that will go in detail on some of these issues. So the first one I wanted to mention and say a few words about is neutrinos. Obviously, the bulk of the presentation will be on gravitational waves. So neutrinos are special because they can provide a very accurate timing on the emission of gravitational waves. This is a simulation by Mike Pakios. And the angular resolution on the direction of the source is not as good for electromagnetic sources, but it could still be used, and I will comment about it during the presentation. Obviously, since 1987, we did not have neutrinos, but it's very important that we have a supernova early warning system in place that is there if we have an important event. Neutrino can be used both for detection and for parameter estimations. I know in rough terms, if the false alarm rate of a candidate event, if you have both gravitational wave and neutrino observation, would be given by the product of the two false alarm rate. And I believe that Marco and Matteo will cover the detail of some of this in their presentation. In terms of parameter estimation, I will go into detail after. Neutrinos, we already know that can be useful, for example, for the characterization of SASI. There are a couple of papers, and Zidou Lin talk will cover this for the neutrino detection. In terms of electromagnetic observation. So they provide the best constraint on the source direction. These are the candidates, for example, for the O3 search. And it's much better than the angular resolution for gravitational wave detectors. And as I'm going to discuss in the talk, they can provide timing information on the gravitational wave emission, even if we have to be careful in how we estimate that. And this is going to be one of the topics where I hope we have a fruitful conversation during this meeting. And estimating mass and distance is going to be important as well from electromagnetic observation. And I already had a very nice conversation with Chris Freyer in the corridors, and I hope you will come to join one of our internal calls in LIGO to talk about these things. Every week we talk about electromagnetic candidates, and I'm very excited if we can understand things a little better. Just to explain a little bit more the issues before I go in a systematic approach in using electromagnetic data. This is the light curve data for 2023 IXF. It was a fairly well-sampled light curve, and even visually, you're able to estimate the time of the sharp breakout, and we call this time zero. It doesn't mean that the gravitational wave is emitted at that time, and it means that sometimes before the time the gravitational wave will arrive at the Earth, but how much before? And that's one of the things that we try to use in the so-called targeted search for core collapse supernovae. We try to estimate a window of time where the gravitational wave could be emitted. I mean, currently, we base internally this estimate on this work by Sean Couch group. Okay.
The one behind Warsaw.
Okay. Sean Couch group, and this is a plot from this paper where there is the mass of the progenitor versus the delay between the collapse and the sharp breakout. And currently we are using an upper limit of 5 days.
Behind here is working.
Oh, okay. An upper limit of 5 days in the delay between the gravitational emission and the breakout. And I'm already, I know, Vartanian talk gave me hope that other people will produce similar plots like this, so we can use them. I know this plot, for example, highlights, at least from our perspective, that if we are able to estimate the mass, we might be able to have this on-source window where we search the data even shorter. So for example, if we would know that the mass is 10 solar masses of the progenitor, and we trust a plot like this, we don't need to have an on-source window that is 5 days long. We might be fine with an on-source window to search data that is just 2 days long, and with benefits in the search, as I will describe. Now, the estimation of the mass is one of the things we struggle internally, and the reason why we struggle in using it, I know I use this case example of the mass estimates of 2023 IXF that we find in the literature. So there is this paper by Pledger and Shara where the estimated mass 8 to 10 solar masses, and Kirkpatrick 11, and then Sorizam 20 plus and minus 4. So pretty much you have all the possible masses, and that's why I don't know, we just give up and use the 5. But so okay, let me talk about the detector response, how our interferometer interact with gravitational waves. And as we go along, I'm gonna comment about how it's tied up with the property of core collapse supernovae. So this is described the basic geometry, I know, of the current L-shaped interferometers, and you have X, which is equal to H plus N. N is our additive noise, and H is the gauge invariance response of the instrument, is a linear combination of the two polarizations, And the antenna pattern depends on this angle psi, which is up there in the reference frame. And what happens is that you have a periodicity of pi, meaning that if psi varies of 2 pi, the antenna pattern varies twice. The response is invariant with respect to the choice of psi, but what you call H plus and H cross depends on the choice of psi. Now, in terms of polarization, I know we have sometimes situations where you can have a linearly polarized signal. So if there exists a psi where one of the two polarization is 0, it means the linear is linearly polarized. This is the case, for example, for the memory. I know if there is a phase pi/2 difference, I know they're elliptically polarized. This could be relevant for the SASE. Now, it's tricky, however, for a network like Hanford and Livingston that are almost aligned, because you can establish the polarization state if you can reconstruct the two polarizations separately. So it might be hard for most locations for Livingston-Hanford. It might be better for a configuration like Einstein telescope. In terms of property of the time series, so the noise is composed by one component that is controlled by the central limit theorem and is the stationary Gaussian noise plus some glitches. And the stationary Gaussian noise has a specific autocorrelation function, and which is connected with the spectrum of the noise. This is a curve that everybody has seen many times. And what I wanted to point out is that there are 3 regions. Is there a pointer here on this one, the top? So there are 3 regions. There is the low frequency part, the intermediate frequency part, and the high frequency region. And the reason why I wanted to point out is because both for current and future configuration is good to know a little bit of the idiosyncrasies of these 3 regions. So the low frequency part, we know that a very, very low frequency, you have the so-called seismic wall, and we have some control systems that try to keep the interferometer in lock. But this control system have some internal resonances and inertia and electric noise that actually dominates the noise at this low frequency. This is called angular sensing control and noise and length sensing control noise. And now the fact that these are mechanical excitation that have some inertia makes them vulnerable in a good way to linear predictor filter to be able to predict some of it and extract it. This is a non-stationary type of noise, but it can have some components that are predicted. And this is the feature that was used in the paper for the detectability of the memory. In the middle range, there is the Brownian oscillation of the coatings. And basically the idea that every atom in the coating has some oscillations. And then if you look at the surface and you do a Fourier transform with respect to space, the 0 component of that oscillation is a coherent oscillation. And temporally is expected to be fairly incoherent. In the high frequency part, you have Poisson shot noise, and is related to the fact that even if you prepare a beam of identical photons that go to a photodiode, the collapsing process is a random process that is controlled by quantum mechanics. And that is intrinsically uncorrelated because every photon doesn't care about what the other photon do. Marianne will talk about the future of the instruments, but I know for supernova purposes, I know improving the sensitivity in different bands require different techniques. So for the coating is one of the hardest part is just trying new material. For the high frequency, which is very important for supernovae, what is beneficial is to increase the laser power and have larger masses. But this is a delicate thing because larger masses means bigger suspension wires, which can propagate more noise through that, and they can damage the sensitivity at low frequency. And now, then there is the low frequency part, which the current status is that LIGO doesn't warrant for any usage data below 10 hertz. And then between 10 and 20 hertz, there is kind of a warning. So it's data that we show that, and I'm going to talk about it for the memory, can have strong interest. However, is data that would probably require specialized detector characterization, is data that we should try to improve. And we can improve it. And there is an upgrade. I know in these times of uncertainty, it's nice to know that there is an upgrade that is actually coming up, I know, in October, and to reduce some of this control noise at the low frequency, to reduce the tilt to length coupling. And so this is scheduled for to happen in October. And the idea is that to have a Mach-Zehnder interferometer that monitors the tilt of one of the end station and use that as a second control loop to reduce the effect of that control noise that I mentioned before. And I know, just had a nice little toy. Okay, so let me talk about detection and parameter estimation, at least in general terms. I'm very happy that I know in the same session you're going to see the talk by Yan. So she's going to talk in detail about the results, but I wanted to put a little bit the perspective in general. So the first question is that I know, what do we do currently? So we currently have two types of searches that are aimed for core collapse supernovae. So there is the targeted search that we currently operate in the case of electromagnetic signature, for which we think we can narrow down the window where the gravitational wave is emitted. And obviously there is the neutrino targeted search, which has not been alerted. And then the supernovae are also searched as part of the all-sky search. And this is aimed for a situation where you might have a failed core collapse supernova that doesn't have an electromagnetic counterpart or a neutrino counterpart, or if we have a poorly light sample electromagnetic curve. I know something that can happen is that if you discover the light curve much later, you don't try to narrow down, because if the on-source window you obtain becomes comparable to the duration of the all-sky search, certain benefits go away. So, so is there a scenario in terms of algorithmic and statistical approach? One question that comes, if someone comes from the senior process point of view, is that, is there a scenario where we know we have some theory that tells us what is the best detection approach and the best parameter estimation approach, and a clear relationship between the two? Unfortunately, there's not much in terms of general theory, but there is one thing. I know we know that if you have a single detector, wide Gaussian noise, and you know the waveform, the likelihood ratio gives you the optimal method. And if you have a discrete random variable, this would be the ratio of two probabilities. Since x of t is a continuous random variable, is a ratio of probability densities. So in the numerator is the probability given the presence of the data, and that depends on some parameter xc, and the denominator, the probability density in presence of noise. The probability density distribution for the case of LIGO has a normalization that doesn't depend on the data. If you would do the same kind of analysis for a neutrino detector, the normalization would depend on the data, because the variance depends on the number of neutrinos that you observe. Now, the typical metric is to take the log likelihood, and in LIGO we have the common approach is that we disregard the logarithm of the normalization, and we only focus on the part that is depending on the data. And in this scenario, we have the Newman-Pearson lemma that says that this quantity it gives you the best detection metric, meaning that you calculate the maximum of this quantity with respect to the arrival time and the choice of the parameters. And the maximum is this quantity. If you apply threshold on that, is the optimal quantity to distinguish signal with noise and to have the best detection probability at a given false alarm probability. And the value, when you vary theta, it gives you the maximum likelihood estimate of the parameters. For supernovae, strangely enough, this is not too far from the approach for the rapidly rotating progenitor, and is also relevant for the memory, for the rapidly rotating core bounce component. And there will be 2 talks about it from Claudia Moreno and Emmanuel Avila. And Coulter talk has already happened yesterday. These 2 talk, can we go back? Or? Okay. So these 2 talk, one is going to be on a frequentist approach to the problem, and the second one is going to be a Bayesian approach to compare the 2. And I will talk about these issues in a bit. So unfortunately, when we talk about real data, we have non-Gaussian component, network of interferometers, and the core collapse supernovae are weakly modeled. I mean, and we don't even know if we have a completely full range of signal, even if it's getting much better. And I'm very excited about Obergaulinger talk later this morning. And so we don't have any theorem for optimality, but the likelihood method is still the starting point for many pipelines that we use or have been used for core collapse supernovae. And we also started recently, we revived recently an effort to discuss how to combine pipeline. We did one at the time of S5, where we learned that we had to be careful about the false alarm, joint false alarm. But now I think we're doing a much better job. Here is a little bit of a garden variety of few of the pipeline out there. I know Coherent wave burst, there are 2 flavors active right now. And Bayes wave is, as it says the name, is Bayesian based. And Spectre, the TF cluster is some historical, I know that's when I started, 15 years or 20 years ago. The Q pipeline is another historical thing that it was the first one that introduced the multi-wavelet decomposition. And the X pipeline that has been used for supernovae, but is currently used, I would say, mostly for gamma ray burst. So how do you introduce the likelihood network approach for a network of interferometers? So the idea is that if you assume that the noise of different interferometers is statistically independent, you just, at the numerator, denominator, you put the product of the probability. This assumption is relatively reasonable for current interferometer, might not be reasonable for Einstein telescope, since you have the interferometer collocated. And, okay. And now, one of the beautiful things, in order to explain the algebra of how someone would approach this problem, it's useful to illustrate it in the frequency domain. So just do a Fourier transform of the data and the covariance matrix. It turns out that the covariance matrix becomes diagonal, and the elements of the diagonal are 1 over the noise spectral density that I showed earlier. The way, so if you want to calculate the gamma, the data is known, but H is not known. And so what you have to do, you need to have a way to calculate H and put it in. And the approach is similar to the variational principle that people use to derive a Lagrangian equation from the action. You do a functional derivative of L with respect to H, which in practice assumes that all the samples are independent variables. And then you convert 17 into 19. That's your nominal solution, and you plug it back in into the H, and then your value of H, you can use that as a detection metric. The problem is that this kind of approach is fairly dry in the sense that what do you use for H? Do you use a whole science run? and so you need to, what you use for, yeah, you need to have a way to isolate small patches of data, D, where D is not the whole science run, but is a small patch of data that we call event, and then pass it to the calculation of the H, and then you plug it in such a way that equation 25 is a quantity that is calculated over a single event. I know a lot of this algebra will be discussed in detail in Sergei's talk. I know, so I'm not going to go through over the details, but 25 is equivalent to have two operators that in the dominant polarization frame, they project the data over two perpendicular directions. And 25 in the limit of large SNR becomes the square of match filter SNRs at different interferometer. As I said, I'm not going to spend too much time on this, but one of the things I want to talk about is what are the ingredients in selecting the events and the optimization of the data that are necessary to work in our non-Gaussian data, and maybe even specifications that are useful for supernovae. So the two that one has already been mentioned is whitening the data, and people have fairly good understanding what it is. I know you can achieve the whitening by dividing the spectrum of the data by the variance at each frequency. The linear predictive filter that I'm going to say more when I talk about the memory has been used in the past, for example, to remove lines, for example, 60 Hertz lines. And the events are reconstructed by doing a wavelet decomposition and form some clustering. And this is an example of how a waveform with the SAS in it looks like. And so you have the vertical line that is the high frequency feature. The red blob is the SASE. If we would have a detection that looks like this, that would be wonderful. The question is that, what if it looks uglier than that? Would the theorist be happy if we choose that the morphology is fine, all internal in the collaboration without discussing explicitly our reconstructed event? So other things I wanted to mention that go into the ingredients of a pipeline are network constraints. So for example, if you reconstruct events separately, different interferometers, you can then check the consistency of the arrival time. The network are going to have a direction where you're more sensitive and less sensitive. Currently, we have at least two groups that are investigating doing a search. For example, in the target case, where we use the location of the electromagnetic source and just get triggers that are consistent with that location. And we have constraint in the time frequency structure. Currently are very generic, but should we do a clustering, for example, that has the shape of the high frequency feature, since it's always there? We also have efforts. I don't think we have talks right now in this conference on using specific talks on using machine learning to distinguish between noise events. And another thing that I'm going to mention later is that there are efforts to even take information from the neutrino and use it for the detection. I think Marco is going to talk about it, but I will have one slide about it. Veto data quality, currently, they are not done specifically for supernovae, with one exception. I know Kaya Schluterman is working now to do specific veto and data quality in the 10 to 20 Hertz band, just to aid the memory searches. And now the detection procedure, what you have to do, you have to produce background triggers. So you have the data, you take data from different interferometers, you put a non-physical time shifts, produce events, and then divide by the total amount of data that was processed, and you produce distribution of number of events versus SNR, or number of events versus false alarm rate, or number of events versus inverse false alarm rate. And the typical distribution you get, a distribution where there is a Gaussian region that decreases very rapidly, and the glitch region are usually the biggest problem to acquire a certain detection confidence. And here you have examples of the predictive background in red, the range of possible background and the search. And what we do, we take the loudest event in the current format, and then you compare with the background, you decide if it's statistically sufficiently significant. And currently, we don't have an exact choice of false alarm rate or false alarm probability that we will require for core collapse supernovae. The first binary black hole was a 5 sigma, similar to the old particle physics requirement. For binary black holes, the first binary neutron star, if you would use a window of 1 week or an on-source window of 1 week, it was still roughly a 5 sigma, but we don't have a decision for supernovae. Maybe it's something people will discuss here. One thing I wanted to talk about in terms of methodology is the differences between Bayesian methods and frequency method. So, so the first thing is that there is a philosophical approach in the sense that for frequentist method, the parameter in terms of Bayesian, they are random variable. But the main point is that the Bayesian approach require a prior. So we can have, we have two possible scenarios. We have a scenario where the theta is property of the noise, and then you can educate yourself on the prior by studying the noise. Or you have the theta is one of the physical parameters. And that's more delicate, because if your theta is the physical parameters of a supernova, how do you choose that? We don't have detection. Sometimes people say, well, we can use a prior that is uniform, and so it's not informative. But let's say you have a paper where you estimate the amplitude and the energy, which is the square of the amplitude. If you choose a uniform prior in the amplitude, is not uniform in the energy. If you choose a uniform prior in the energy, is not uniform in the amplitude. And so our new spokesperson, the LIGO Virgo collaboration, Steve Fairhurst, did a paper recently with one of his students to show that the choice of the prior is a delicate aspect that can impact parameter estimation. And so we should test at the very least that the prior that we choose, if we do a Bayesian approach, do not impact the parameter estimation. And Emmanuel talk will actually cover that. In the past, there have also been situations where the priors produce a parameter estimation with a variance which is smaller than the theoretical minimum that you can have, the Kramer-Rao lower bound. And here there is a reference where I discussed that. But in the case where the prior is about the noise, it's a fair game. Sorry, I think I went the wrong direction. And for example, this is an estimate by Bayes wave of a waveform, where the waveform is estimated by just looking to what is inconsistent with the noise. And so it does give you the waveform, it doesn't give you the two polarizations. Okay, so the last comment I wanted to make in terms of methodology, and maybe then I'm gonna take a little break for the first part, I guess, is how do we treat calibration errors for supernovae with respect, for example, to binary systems. So historically, the approach has been to quantify the calibration error in terms of amplitude and phase, and check the impact by jittering the amplitude and jittering the timing. If you have a narrowband signal, doesn't matter what is the frequency dependence of your calibration error, everything converts in a jittering amplitude and a jittering timing. However, if you have a broadband signal, for example, here, if you have something that is a jitter in timing, you need to have a very specific dependence of the phase error in such a way that the same waveform untouched is shifted in time. These curves here describe the type of calibration error that we have in phase, and they don't follow this trend at all. And you can see the talk by Mill and Wills about this. And so this means that supernova waveform can have the shape distorted. Anyway, so I think this is a good point to stop for the first part of the talk, and then take a few questions or a break, and then I will go to the second part of the talk.
Who wants to kick off the questions?
I think like people know already all of this.
Oh, it's always good to be reminded, even if you do know.
I have to admit, I don't know this calibration error stuff at all. Could you expand on this a little bit? Is this calibration between the detectors, or what is this error?
So the gravitation waves arrives, and what the detector measure is an optical intensity, and it doesn't measure directly the strain. So you need to convert the optical intensity into strain, the HOT. So how do you do it? With a convolution of a response function. Now, this convolution is not exact because the interferometer constantly evolves. And so we periodically, at different frequency, for example, we have calibration line where we excite the detector at one frequency and then another frequency. We excite with a certain displacement, we see which optical intensity produces. Then I do on another frequency, then I do some interpolation between the frequency and I reconstruct the transfer function. But this transfer function changes with time and has some error that we constantly monitor. Sometimes, usually we try to keep them to a few percent, sometimes we are not as lucky. But the message is that people that are familiar with this calibration error impact are more familiar to the fact that it doesn't have the capability to distort the signal for CBC signal because it's roughly one frequency at a time, while the time frequency volume of supernova is larger.
Thank you very much for the talk. Can you go back to page 24?
Okay.
So can you remind me why you mentioned that this red spot is from a SASE, right? So can you explain again why SASE has stronger emission than the other fundamental modes?
Oh, so this is a representative waveform. This is from the Kuroda waveform. And now, in this case, the wavelet component became stronger. You might say, well, if I do a brute force spectrogram, it will never become stronger. However, let's say that you have a wavelet that is exactly the duration of the SASE and exactly the band of the SASE, is going to have a very large amplitude, that wavelet. On the other side, if in the G mode, the wavelet only capture a little chunk of G of F mode, it might give you the impression that it's weaker. So this is not how it would look if you have a regular spectrogram. This is how it gets mediated by the wavelet decomposition.
Okay.
Okay.
Thank you.
Michele, can you remind me, go back to the detector response slide?
Yeah.
I just want to make sure I understand when you say that it's invariant.
So the quantity H, what is
yeah,
it? Okay.
is it in, under?
I think it's back early.
Yes, a little bit. Yeah, just is it under changes of psi?
Yeah.
Or,
Yeah.
but not theta and phi, right?
No, just change it up psi.
Psi. Okay.
Yeah. You can change. What happens is that the H plus and H cross, you transform it with the rotation matrix, which is the inverse of the rotation matrix. You transform the antenna pattern, and the H is invariant.
Thank you for the very nice talk. So I just have a question about SM 2023 IXF, where you mentioned like the mass estimation is like a broad range. Can I know what is the impact of like the mass, like knowing the projected mass on like the search sensitivity? Like, does it matter?
So, okay, so
Thanks.
this is when we have an event, we want to try to understand if it's a compatible event with the supernova. So the more we can learn, the better. I know the problem why sometimes we have incompatibility, my understanding is that some groups estimate the mass from the early part of the light curve, and some group use the plateau. Is a different methodology that have different idiosyncrasies, and often, unfortunately, they give inconsistent things. Now, in our case, the impact is that if we are not sure about the mass, we are very conservative in the on-source window duration. And but in terms of the energy, I know in this talk, in this conference, there have been discussion about, do you expect the core, the convective phase to be stronger for stronger masses? So there are other morphological features that might be different that we could use. All I'm saying that for the specific targeted search, we use it just for the on-source window.
Any more questions? Maybe I can ask one. So far we've had to calculate quite big on-source windows for the gravitational waves we've done targeted searches for. But if we have a neutrino detection and we know the exact time of the signal, how much is that going to help improve our search sensitivity?
I'll cover that in the second part of the talk, if it's okay.
Okay.
I have a slide on that. Ready for coffee? Resume in 15.